right? I hope that you can see my screen. So the course title is Visual Computing, and probably you may already know that this is a very broad area, right? So the image processing and also typical computer graphics and simple visualization and almost anything that you are doing for creating or maybe acquiring or maybe regenerating or visualizing whatever it is, right? Regarding visual data, it's called visual computing, right? So you have visual data, right, or some numerical data, and then if it involves in something that you can see, so then and it involves in some computers to do something with this data, then it's called visual computing. Now, anyway, even though it's a broad area, under this particular course, we are going to just tackle the visualization part and also some basic theory inside this visualization, combining with the knowledge that you gained previously through the computer graphics, right? So I will give you some brief introduction, right? So these are the course objectives, right? You are going to acquire knowledge of basic image synthesis and image analysis principles and algorithms. So part of this image analysis you will going to get when you are doing image processing for your special course, right? And the others you will get brief knowledge, and then you will learn you will learn the theoretical knowledge in computer graphics to display realistic 3D images, and also you will gain some experience in clustering and classifying real world data because it helps you to visualize, right? So basically here we are going to discuss just visualization and underlying theoretical background, right? So this is the content, and you may be familiar with some of these content, right? For an example, shading principles. Have we discussed shading principles before under computer graphics? Yes or no? Anybody? Yes, we have done. Yes, you should have been should have uh, done shading principles, and I will just recap quickly what the things that we have already learned, and then we'll get into the additional part, right? That is, I think you may have not completed the shadows, right? So I will get into the shadows as well, and in addition to that, probably we will be able to get into the much more details regarding how do you get the values out of when you're mapping the information to this whatever visualization. And you may have not done polygon filling algorithm, so we are going to discuss the polygon filling algorithm as a kind of thing, some kind of thing within the rasterization. Isocurve and surfaces, okay, you may have not heard about this one before, or may it's not actually included in your previous courses. Marching cube algorithm, again, it's a new thing. Volume rendering, probably a new thing for you. Ray traversal scheme, sometime you may have heard about this, right? Part of this has to be done when you are doing Z buffering or maybe the hidden surface removal algorithms under the computer graphics. And then scientific visualization, information visualization, and data visualization. Maybe you may have discussed those who have done statistics, right? You may you may have done go through some of these techniques that we are going to discuss under these three topics: scientific, information, and data. And image morphing, right? I think this is going to be done even in digital image processing, right? But anyway, here we'll discuss some underlying theories, right? Some algorithms, and then virtual environments, right? So in addition to these things, I'm planning to give you some brief introduction on algorithmic cards, right? So we'll discuss them later, right? So this is how you are going to evaluate it, right? The assignments account for 30%, and the semester terminal examination is a written examination, and it's account for 70%. So I cannot predict whether it's going to be exactly the same as previous examinations, and because the uncertainty of the country. So we'll see, right? But we can do sometime. Maybe the evaluation can be slightly changed, right? Keep that in mind. But there will be definitely continuous assessments, right? So keep that in mind. So complete the assignments on time, so you will get the marks, right? And here's some references. I will give you this slide so you can later refer these things. Right. So anybody have any idea about this image? Can you explain the content of this one? It's a pattern, right? It's a kind of eye pleasing pattern. And any more details about this pattern? Anybody? Well, anybody know the name of this pattern? Or the type? Yeah, it's fractals, right? Have you learned about fractals before? Somewhere else? It's a fractal art, correct? Or fractal pattern. And what it is? And anybody have learned about this before, or for the curiosity, you learned it? Maybe you may do self-learning. It doesn't matter, right? Or maybe sometimes, right? This may be, yeah, great, right? So just out of curiosity, you may, okay, that's great, right? You can just search for these kind of things, because this is very kind of very eye-pleasing pattern, and it's again a very complex pattern, right? If you look closely, it's extremely complex, and this can be infinitely enlarged, right? This can be infinitely enlarged by redrawing it again and again, and you will find different kinds of patterns, right? A slightly different kinds of pattern, and it actually you can encounter infinite number of patterns, and if you go through all the way, traverse through the spatially, and at the same time, if you just zoom in, right, continuously. So how we are going to put all this information, right? Since it's a really large amount of information, it's really it must be really hard to put all this information or represent this information within a computer, isn't it? But not really like that, right? If you go through this image, right, and if you just keep enlarging this one, you can see these uh, features within this image, right? It looks kind of a swirl, and also there are much smaller swirls at the edges of this image. Can you see? It's a kind of a swirl, right? මේ edges වල තව තියෙනවා නැවතත් ඒ වගේම swirls තියෙනවා. And it has different shades of red, and outside the middle area you can see some green shades, right? And in addition to that, there are some purple dots, right? And they're actually swirling over it's not kind of a directions clockwise, to the clockwise direction, and some highlights, and yeah, you can see lots of different colors here, right? And if you like, since this is a kind of a computer generated image, you can actually put more colors as well, right? So how this is possible, right? How we are going to create this kind of very complex image, right? Very complex visualization using a computer programs, right? So the algorithm must be very complex, isn't it? But the reality is it's not, right? So the very pattern that you just saw is called Julia set, right? It's actually a fractal, right? Fractal is it's a class of algorithmic cards, right? So you can run an algorithm, very simple algorithm, and then you can create that particular pattern, right? So in reality, this is what we are running. This is actually iterative function, right? And if you really check this one, you will be able to see this is nothing but a recurrent function, right? Here you have Z, right? And Z is actually what? Z is actually a complex number, probably like 2i, right, plus 5, right? Okay, this number is actually not 2, right? It should be some very kind of a small one, but doesn't matter, right? Whatever the number you are giving you will get a different pattern, right? Right. So something like this, right? I stand for, actually it's a complex number, so you know what is this, right? It's a kind of square root of -1, something like that, and that's it. right? So this Z square is again a kind of, the same thing, right? The same complex number, and C is a kind of a constant, but it's a complex constant. Again, something like, yi plus x, right? Something like, sorry. So basically that's what you need to create this complex art, right? So when you change this one, right? When you change this one, you will get, different patterns, right? Because the whole image will be shifted somewhere else. And also, this has to be, this Z has to, you can change this Z, right? For each and every pixel. Now, in reality, this can be done by using assigning the pixel value, right? Now here you have 0, 0, 0, 1, 0, 2, 0, 3, likewise. And here when you get the, let's say 100, 100, 500, 500, likewise, just X and Y coordinates, right? So you assign this X and Y coordinate as the X and Y of the real part and the imaginary part of this Z, right? Plus this constant can be, it's a user defined one. And then you keep doing this by considering kind of a radius, right? It's called radius because you keep doing this while you are checking the Z, right? The norm of the Z. Maybe you know this one, right? අපිට complex number එක ගන්න පුළුවන් මේ magnitude එක. So we are checking this magnitude is less than some r, right? හැම pixel එකටම මේක loop කරගෙන ගියාට පස්සේ මොකද මේක ඔයගොල්ලන්ට පේනවා ඇති fc z is actually z squared plus c, so you get another z, right? So then you use that z to do this again and again, right? And then you are doing this until you have this, right? The norm of this z is less than, or it's actually greater than, right? You can be r වලට වඩා වැඩි වෙනකන් ඔයා මේක කරන වැඩි වෙච්ච ගමන් ඔයා නවත්තනවා. එහෙම නැත්නම් මේක අඩු වෙනකන් ඔයා මේක loop එක කරනවා වැඩි වෙන ගමන් ඔයා නවත්තනවා. Right? So then you are counting the number of iterations that you have to go through this, and this number of iterations, let's say you do these 5 iterations, so then you are converting this 5 into a color, right? So basically you can run this one up to maybe just 255. So you can put shades, right? 0 means black, 255 means white. So you can do this, and for each pixels, because you said this actually simply X and Y, then each pixels you get a different color. So that's when you assign it here. So this is what you get, right? It's simple as that. So that means even you can implement it within just 5 minutes or 10 minutes. You can simply implement this one using, whatever the language that you like, right? Which supports GUI, then you can implement Java, C#, whatever it is, right? So this is just one arithmetic, sorry, this is called algorithmic cards, right? Which use kind of an arithmetic calculations within the algorithm, and at the same time the name is Julia set, and there are other types as well, Mandelbrot and a couple of others, and other now there are more algorithmic cards outside the Fractal as well, right? Fractal is just one algorithmic card, maybe okay, cell automata, right? Is another one, right? We will discuss them later. Anyway, so this is just one application, right? Or just kind of a visualization which you can get, right, using computers, right? And if you want more detail, just go for, there are nice articles in Wikipedia, right? So you can start there, and then you can start even implementing, and if you really like. So there are a couple of advantage of learning about fractals. So because fractals are used for just visualization, and at the same time to understand the real world the things, right? I mean, physical ලෝකයේ ගොඩක් දේවල් අපිට remodel කරන්න පුළුවන් fractals වලින්. එහෙම කරන්න පුළුවන් වුණොත් ඔයගොල්ලෝ දන්නවා ඉතින් මේක කොච්චර ලේසිද කියලා. කියන අපිට දැන් අර සම්පූර්ණ complex දෙයක් අපි මෙතන පෙන්නනවා නම් මෙන්න මේ වගේ පොඩි equation එකකින් අර වගේ complex image එකක්. ඒතකොට දැන් physical ලෝකයේ තියෙන සාමාන්‍ය phenomenon ගොඩක් complex, අපිට මේ වගේ පොඩි equation එකකින් පෙන්නන්න පුළුවන් නම් ඒක සෑහෙන වටිනවා. මොකද ඒක පස්සේ පාවිච්චි කරන compression වලට, right? One thing is for the understanding, other one is for just for the compression aspect, right? It's almost like you compress this whole image with bunch of colors and also bunch of the different patterns in different scales, kind of an infinite data into just single line of equation, right? So the compression ratio now. Okay, that's about the fractal, and just dig into the deep. Okay, this is another one, right? Kind of a visualization which gives you a bunch of information within the same image, right? Different colors, and also there are some, dotted or maybe kind of a blob-like information. So we'll see what it is. It's a kind of a terrain geometry, right, with bounded texture, and also it's not only having just kind of a static data, right? It might have kind of a temporal data as well, but the problem is you can't see. It's not a kind of an animation, right? But using the temporal data, we may calculate the directions. Let's say this is wind directions, or maybe wind mapping of on top of the terrain, which overlaid on top of a kind of a terrain visualization of some kind of a geography, and then this can be this can be visualized through arrows, right? So the actual information, the numerical information looks like this. Why? The terrain geometry can be represented in terms of bunch of points, right? We call them as a point cloud in three-dimensional space, right? So the point cloud actually consists of, 3 coordinates for each point, and you will have a bunch of points, right? Maybe millions, billions of points. And then you have this terrain texture. So texture mapping also can be done by using some kind of a coordination system. This is probably again 3D, right? And in addition to that, we have this temporal data, right? The time 0, that means unit 0 time and the unit 1 time. So you have different, volumetric cloud cover, and also the wind vectors. So these actually information or the data that you acquire from kind of a real world phenomenon, right? So if you have these things, right, then you should be able to visualize all these information. Now you may have millions of information, so you cannot simply go through all this data, isn't it? Data so the best way is if you visualize these things, then you be able to get some idea. So one challenge of this data, which cannot be which can't be just go through one by one, is first of all the quantity, right? Quantity ka godak lokoi. And the other thing is, this individual data sometimes does not mean anything. Again, එක data point එකක් ගන්න බැලුවට ඒක information එකක් ගන්න බෑ. So you have to just grab at least maybe 100 to maybe 1,000 points, and then you can get some information, right? Because they have some correlation, and also they may give you some noise as well. But when you look at the overall data, then you can simply drop the noise, right? Outliers, and then you can get some idea from the majority contribution, or the contribution from the majority of these points. Anyway, so this type of data is called spatial temporal data. Why? You have this spatial information and you have this temporal information, right? So basically you have different spatial information that has been captured in different time instances, right? So it's a wonderful process when you are converting this temporal spatial temporal data. It's called as a spatio-temporal data into kind of a some kind of a, it might be spatio-temporal and then chromatic, right? Some other chromatic visualization colors we are creating kind of a visualization, right? So this is a kind of a visualization, right? It can be an animation, and here it shows just one instance of the whole phenomenon, or the captured phenomenon, and it shows the wind and also some kind of a isochromatic lines, and also the wind vectors can be shown using just an arrows, a bunch of arrows, and all this information laid on top of a kind of a terrain, right? A geographic terrain. So this is called GIS, right? Geographical Information System. And you keep all this information within the database, and then you are converting it to visualization, overlaid bunch of layers, one on top of the other, and then you can visualize them. So just one picture, there are lots of information that you can capture from this visualization. Another visualization, right? Ethnic communities and regions, religions, right? Population density and land use and economic activities. So, well, anyway, we are not going to do GIS here, right? So we are actually going to discuss the underlying theories and technologies. In case if let's say you are going to develop a CAD application or maybe kind of a GIS application in the visualization part, then as computer scientists, you will need this information, you will need this knowledge to create a program, not to use the program, right? Using these things is a kind of it's a different different area, right? ඒ කියන්නේ GIS කියන එක different area එකක්. දැන් GIS වලට tool එකක් හදනවා කියන එක ඒක වෙනම area එකක්. So we are the one who actually develop the things, tools for these applications, right? We are not the one who actually use these applications, but anyway, we can actually utilize our knowledge to even use these things as well, right? Doesn't matter because some of these fields, usage of these fields actually comes under the computer science. Doesn't matter. Another visualization, right? The Sri Lanka tsunami damage affected area, the water height. It's actually kind of probably the altitude, right? It shows some isocontours, right, with the geographic information. Right, so if you check what is visualization, it's nothing but transformation data or information into a picture, right? So because final output will be just a picture. We really don't, we really don't need to call it as a picture, right? It's better to use the term image, right? It's a bunch of pixels, right? That's the image. So you are transforming data, information, right? Data means if you are just acquiring some numerical values out of a kind of a phenomenon, it's called data, right? And if you can do some kind of processing and then you can extract some, something called some again kind of a numerical representation, but you can give a name for that, right? You can simply give a name which can be understood by human, then it's information, and then you can just create a kind of a visualization which you can see, not the numerical values, but you can see them in a different form, right, as a picture or maybe image, right? So that's why we do this course, right? Visualization. And anyway, it engages the primary human sensory apparatus, that is a vision, right? Your eyes. And it's a tool for mainly for learning and understanding, right? It's an aid, right? Not direct tool, but it's a tool for aiding for learning and for the understand, right? If you have large number of data, then if you want to understand it, one of the first method is that if you can just get, if you can just visualize it, then you can understand it easily, right? And also you can even reveal underlying patterns, right? සමහර data තියෙනවා අපිට ඇත්තටම තේරුම් ගන්න බෑ කියන අපි දන්නේ මේ data අපිට දෙන්නේ මොකටද කියලා. නමුත් data එක දිහා අපි visualize කරොත් සමහරවිට ඒකේ underlying patterns අපිට පේනවා. Patterns වලින් අපිට මොනවා හරි knowledge එකක් අපිට generate කරන්නත් පුළුවන්, right? And the compact representation of information, right? If you have large number of information, then again this will be a kind of a tool, right? And also is a kind of a carrier of information. For an example, weather forecasting, right? It's a kind of information, and it's actually conveyed not just by verbally but also with visual aids, right? So the visual aids help the people to perceive the information or convey the information more effectively, right? Cutting කියනවට වැඩිය ලේසි, නැත්නම් ඊට වැඩි ප්‍රමාණයක් අපි ග්‍රහණය කරගන්න. Retention is higher when there is a visualization, right? Not just the audio but also the visualization. Okay, bunch of flavors are there, right? Scientific visualization, data visualization, information visualization. They have kind of an intersection, right? But you can see kind of a different it's called definitions, let's say, right? Scientific visualization includes user interfaces, data representation, and we learned there are some processing algorithms, right, and so on. And data visualization, it includes financial data, and we can use statistical methods to reduce the data, and then you can visualize them, right? And information visualization includes, let's say, abstract data like simple hypertext document, right? Or maybe we can visualize file structure and maybe some arbitrary relationships of data, right? So these are just three main flavors, and we are going to go through all these three flavors throughout this course. Right. So history of visualization, 1137, right? Or kind of a, you can see, you can actually Google this one. I can't remember the name of this map, right? This one. This one, right? So it's this kind of an earliest known map. I think this is not the earliest known map, but this one is the most accurate, right? Or whatever the accuracy, which is very closer to the today's map, right? Found in the history, which is found in actually China, right? And just type this, the year, and also just type earliest known map in China, then you will get into this map, right? And 1603, the first star charts by Johann Bayer and Cartesian coordinate system, right? By 1637, this is one of the it's a kind of milestone, right, for graphics, right, geometric, and also it's a kind of something that we are mainly used or frequently used in even computer science, right, for graphic related stuff, not just graphic related, but also many other aspects. Right, so these are just a couple of applications. So this is called isotherms, right? Isotherms, or it shows you the lines which gives you the same temperature and laid over a map, right? Geographical map. And isochromatic lines, right? You have first map some of the features of this, whatever the surface into a kind of, different colors, and then we just connect the similar points or the similar colored points, and then we draw lines. So these are called isochromatic lines. And isobars, right? So bars stand for, we are using the unit bar for pressure. So it actually gives you the pressure, right? The same pressure points when you are connecting the points with the same pressure, then you are creating isobars, right? So why we are doing this? Because this is nothing but kind of applications. So we are going to learn the underlying theories behind how do you draw these isobars or whatever the isocontours by norming the values for the data. And yeah, 3D imaging, right, is another part of this visualization or the visual computing, right? So the Roentgen found X-rays accidentally, right? And then Mackenzie and Davidson found stereo X-rays, right, which gives you the depth as well, right? And then X-ray sections or slices, right? So you can now get a complete 3D volumetric data, right? So it's different, right? The 3D data and the volumetric data is different. So how they differs? Anybody knows the answer? What's the difference between a 3D and also, let's say, X-ray sections or X-ray slices or volumetric data, and the other one is just a 3D object and volumetric object. So what's the difference? Any idea what's the difference? Okay, we can rotate within an axis 4, 6, 8. You can rotate, right? It doesn't matter whether it's an object, a 3D object, or maybe kind of a volumetric object. It's possible, right? Both are giving you the space to rotate, right? We have the opportunity to whatever the given axis, you can rotate them. That doesn't matter. So that's a kind of manipulation for whatever the 3D object. So it's not the difference. What's the real difference? This should know those who do, 3D object modeling, maybe using Maya, 3D Studio Max, Blender, whatever it is, right? If you are designing, if you are doing a 3D design, then you should know the difference between volume data or the volume kind of a volume 3D and also simple 3D objects that you found in kind of a Maya like software. What's the difference? Well, the real difference is there's nothing inside a simple 3D object, right? 3D object එකක් ඇතුලේ මුකුත් නැහැ. You are just modeling the surface, right? There are a couple of ways of modeling 3D objects. You can use polygonal modeling techniques, or maybe you can use surface, or maybe NURBS modeling technique, non-informed rational basis of spline, right? NURBS gonna පාවිච්චි කරන්න පුළුවන්. But that doesn't mean you have something inside, right? The inside data will not be there, right? For an example, if you just create a skull of a human, right? Or maybe let's say a body of human, right? A torso, then you can see the human body from outside. But if you just move your camera inside, there's nothing, right? No internal organs. That's how it works, right? Unless you create them specifically, right? You can then you can redesign the again design the internal organs, and then you can place them again. If you go deeper into those organs, again there's nothing, right? You can't find vessels, flesh, and other things unless you create them. So the difference of this volumetric data, or maybe kind of volume object and typical 3D object, is both are 3D, right? Both can be shown in 3D space, but volumetric data, if you dig into the deep, then you can find its inside matters, right? ඇතුලේ තියෙන දේවලුත් ඔයාලට බලන්න පුළුවන්. If you create a model, volumetric model of this earth, right? sphere එකේ model එකක් හදුවොත් ඒ volumetric, then in computer you can slice it, right? When you slice it, you can see what's inside the middle, right? The crust and also the core, right? The magma, everything should be seen within that model. So that is called volumetric, right? Or the volume 3D. It's a volume, right? ඇතුලේ තියෙනවා ඒකේ අර අපි කියන්නේ inside data ඒකේ තියෙනවා, right? So these sectional x-ray or maybe slices of x-rays are actually something like that, right? So instead of you are just getting just one single plane, you keep increasing the current for the x-ray machine, right? The x-ray beam, and then you keep imagine different slices, the different depth of the flesh or whatever the component that you are going to imagine. Then when you combine all these things together, you will get actually 3D object, which is not simple the surface, but also which includes the internal parts as well, right? So basically then you can see and you can go through the slices and then check the different cross sections of whatever the organ that you are inspecting, right? And X-ray crystallography, and it uses positions of atoms in a crystal. This is actually used for analyzing different components, chemicals, and mostly proteins, right? Okay, let's go one by one. X-ray, right? Just sections or multiple slices. Human skull, right? Because some absorb and some penetrates. So when you invert, then you will be able to get this kind of image, right? So due to the penetration feature, the penetration capability of this X-ray, you can just penetrate the flesh and then get into the bones, your teeth, and whatever the other solid matters, right? And based on the current, you can actually imagine different components, right? If you want to see the flesh, right? Again, මෙතන bones නැතුව flesh විතර බලන්න අවශ්‍ය නම්, then you can adjust the current. And when you reduce this noises, then you should be able to see the tissues, right? And more the current, you can you can just see the bones, right? And other rigid matters. And this is X-ray crystallography, and this is small small mistake, so you have to place the sample here, right? Water that sample within the right? And then using the X-ray diffraction using a crystal, then and with this X-ray detector, then we can actually get into the electron density maps, and then the density maps can be converted into the protein model. It's actually kind of a prediction technique with very kind of average accuracy. So basically, you get the protein model. So why it is important getting into the protein model? Well, you will learn, right? So when you visualize this protein, whatever the protein or maybe amino acid sequence, then it's really helpful, beneficial to know what kind of protein, or what kind of reaction, or what kind of the mechanics that the protein performs, right? So you may learn this one when you do the bioinformatics, right? I'm not sure whether you get the chance, right? But if you get the chance, then you will learn why it is very helpful uh, to to know the structure of protein, right? කෙටියෙන් කියනවා protein structure එක තමයි ඒකේ mechanism එක decide කරන්නේ, right? ඒ කියන්නේ ඔයගොල්ලෝ බැලුවොත් එහෙම ඒ කියන්නේ අපි හිතමු නයි විස එහෙම නැත්නම් සර්ප විසක් ගත්තොත් මේකත් protein එකක්. එතකොට ඒකත් සම් ගොඩක් වෙලාවට ඒකේ තියෙන මේ හැඩය අනුව structure කරන අපිට කියන්න පුළුවන් මේක poison එකක්ද නැද්ද, කන කෑමක තියෙන එකක්ද, එහෙම නැත්නම් අපි gene එකකින් produce කරපු එකක්ද, ඇඟේ ඇතුලෙන් හදන එකක්ද මොකක්ද කියලා හඳුනා ගන්න පුළුවන්, right? So this is done by using computer graphics, right? So we are using computer graphics over this X-ray detector, or whatever the X-ray detector produces. Then we use computer graphics in order to generate the electron density map. And I told you about this volumetric data, right? So volumetric data is nothing but, again, I'm telling you, you are just visualizing each and every volumetric data graphically, right? So as you can see here in this one, you can see the flesh, right? And inside some bones, right? And even inside the bones, you can find sometimes the surfaces of other organs like eye cavity, eye bowl, right? Even inside the water bag, right? And other things, right? And here another part, right? Volumetric data. So not outside data is not absent here, but the ribs and the other skeletal data, right? And part of the vessels also available here. And here you have some the kidneys as well. And another volumetric representation, visualization. The flesh is there, the skin also there, and here inside it you can find the veins and also the tunnel nerves, right? So carpal tunnel, I guess so, I'm not sure, right? And so these are the domains, right, that you can find within the visualization. So volumetric data sources, they're typically produced by scanning devices, right? Computation, right? Or maybe mathematical, or maybe simple measuring, right? So any of these three typically generates simply the data which can be projected into 3D space, right? The thing is, they are not typically placed within the same surface. Instead, they placed inside and outside, or the surface and also the inside, both together, right? So there are a bunch of scanning devices, right? One is simple X-ray machines, right? And some ultrasound also can be used, right? Ultrasound is a kind of a scanning device. Computational or mathematical is a kind of simulation, right? You can simulate the stuff and then you can regenerate volumetric data, and then you can even measure, right? So you can use simple, without using a kind of a scanning device, you measure it, right? අති මොන manually measure කරන්න පුළුවන්. Manually measure කරාට පස්සේ මේ measure කරපු data ටික ඔයාලා ලියාගෙන එහෙම නැත්නම් feed කරලා computer එකට ඒකෙන් ඔයාලට හදන්න පුළුවන් visualization එක. Right. So visualization as a toolkit. So what are the application? So these applications usually coupled with the haptic feedback devices. Okay, what is haptic feedback? What is this haptic feedback or haptic feedback device mean? Well, it's okay, right? You can unmute yourself and you can answer the question. And if you have trouble in using the microphone, then maybe you can use your, the chat box or maybe the conversation box. Yeah, what do you think? What is haptic feedback? Yes, it's kind of yeah, touch and motion. Yes, haptic feedback means actually it's the core, right? You touch, and by moving it, then you get some kind of feedback, right? It's a kind of a sensible feedback to your skin, right? Maybe kind of a vibration or maybe kind of a shaking, right? Those are haptic, kind of haptic feedback actually, right? One example is, I'm not sure whether you're familiar with, there was a one version of iPhone, right? With that, that iPhones typically comes with single button earlier. Now there are no buttons anyway, but those earlier one, I remember there was one model came with a haptic feedback enabled button, right? So when you press that button, you really feel it like uh, you pressed it deep, right? ඒ බටන් එක press වුණා වගේ දැනීමක් තමයි අතට එන්නේ, right? But in real it is a non-mechanical button, right? So there is no mechanical part. ඒ කියන්නේ ඔයාට ඇතුළට ඒ බටන් එක ඔබන්න බෑ. ඒ බටන් එක rigid බටන් එකක්. ඒ කියන්නේ rigid surface එකක්. ඒක එහාට මෙහාට යන්නේ නැහැ. ඒක හෙලවෙන්නේ නැති බටන් එකක්. Or maybe it is moving, right? It is iPhone 7 and 8. Okay, so you know it, right? It may be slightly moving or maybe giving some kind of a a vibration, right? But you feel it like you really pressed it, right? That's a kind of haptic feedback. And there are many other applications available, right? Probably simulation. අපිට සිමියුලේට් කරන්න පුළුවන් haptic feedback වලින්. ඒකට අපිට ඇත්තටම equipment එක අදාළ environment එකේ නොවුනත් සමහරලාට environment එකේ තියෙන දේවල් අපිට haptic feedback through දෙන්න පුළුවන් අදාළ user ට, right? ගොඩක් simulation training applications තියෙනවා, right? But anyway, they are typically coupled with this visualization, right? Because then you can enhance this feedback, right? සාමාන්‍ය haptic feedback කියන එක දැනෙන දෙයක්. එතකොට දැනෙන දේ sense එක enhance කරන්න පුළුවන් අපිට තව ඒවත් එක්ක එකතු වුණාම. ඒ කියන්නේ visualization එක වගේ එකක් එකතු වුණාම. And stereo output like glasses, these are actually for the augmented reality. Google glasses, if you don't know about the Google glasses, just search for the Google glasses, which is kind of a discontinued product. But anyway, I assume and I can predict that it will be in the market in maybe sometimes in future, not as Google glasses, maybe with different name, right? And also the interactivity, yes. And all these things, right? Whatever the things that is coupled with the visualization or visual computing, right? They demand rendering algorithms, right? So this is some haptic feedback device, right? Right. So these are some scanning domains, right? In medical scanners, you can find MRI, magnetic resonance imaging, computational tomography, and single photon, right? Electronic or electrical tomography, computational tomography, right? And positron tomography, positron emission tomography, ultrasound, right? So MRI typically used for probably visualizing brain activity, right? There are other variations as well, fMRI, functional MRI, which gives the functional aspects of the brain if you use MRI. And MRI even can be used with other organs as well. CT also used for mainly inspecting brain and other organs of human, right? And there are other equipments available, scanning equipments available. These are just very few, right? Scanners which typically used in hospital or medical care centers. There are new equipments available, right? I recently found which actually uses a kind of a temperature, which is not the simple tomographic scanning equipments that we used currently. It's a new one, right? But now it's available in hospitals as well, and many research now currently doing over the enhancing and also acquiring more information out of the products of or the outputs of these imaging applications, right? Well, the kind of a tomography, and maybe you know this one. This is ultrasound, and I'm not sure whether you know about the things behind the ultrasound, but ultrasound is, it's a kind of imaging technique which gives you almost the noise than the signal, right? The very lower signal to noise ratio, and we can barely see the stuff using the ultrasound. But thanks to the computer scientists, right, and also the engineers, right, we can see, right, we can enhance this image. Now we can even create 3D models of the object that we are scanning. One example is babies, right? We typically use ultrasounds to scan the fetal growth or maybe the behavior of the fetus. So nowadays we can actually use many dimensional scanning, right? I use the term many dimensional because it's growing, right? We used first of all 2D, actually 1D was there, 2D was there, 3D was there, 4D was there. Now we do 5D as well, 5-dimensional ultrasound scanning, and it's now creating even the 3D models, right? It's actually kind of using surface rendering technique, and using ultrasound we can even do volumetric rendering as well. But anyway, it's the advancement, right? If any of you would like to do higher studies, maybe doing a PhD, Master of Philosophy, kind of a research degree, then this is kind of a field, right? Because there are still a bunch of opportunities that you can contribute to this, ultrasound or maybe whatever the imaging technique where enhancing is required, right? Specifically, the CT, right, which uses X-ray. Maybe that X-ray is harmful for bodies, right? So if you can use less current, right, to X-ray, then it produces less dose, right? Dose එක අඩුවෙන් අපිට X-ray එක පාවිච්චි X-ray එකේ dose එක ගොඩක් අඩු නම් අපේ තියෙන harm එක අඩුයි, right? But lower the dose produces more noise, right? Lower the dose, more noise. Higher the dose, better the imaging, but again really harmful for the body, right? සාමාන්‍යයෙන් ඔයගොල්ලෝ දන්නවා ඇති permitted dose එකක් තියෙනවා පුද්ගලයෙකුට අවුරුද්දකට සමහර රෝගීන් ඉන්නවා. ඉතින් ඊට වැඩි සමහරකට කරන්න වෙනවා. සමහර රටවල නම් X-ray එකක් ගන්නවා කියන්නේ අන්තිම. يعني අවසාන එක තමයි X-ray එකක් ගන්නවා කියන එක එච්චරකට ඒක harmful අපි දන්නේ නැතුණාට. මොකද අපේ ජීවිත කාලේ කොටසක් අඩු වෙන ඇත්තටම. Right? The more you expose, the less you have to live. So because of that, there are a couple of research area which if you can enhance the image, right? Even with with the existence of the noise, you even can see the actual signal by using enhancement techniques. So that would be better, right? Because you can still use lower dose and then you can still get a better image, right? So there are space, right? Even I was working kind of a research, collaborating with some Malaysian experts. It went well, but still we found that there are future enhancements. So it's a kind of a direction for you, right? Maybe any of you have ambitions to get involved in the academics or maybe higher studies, then this is a kind of area, right? Okay, so medical domain, you can find vein weavers, right? So this is again a kind of fancy device. I have not seen this one in Sri Lanka, right? Anywhere, any hospital, but this is very useful application, right? Which utilizes very simple mechanism, right? You can do this by using a simple projector plus, IR, right? Infrared camera. So any camera is nowadays infrared camera, right? Because it should be CMOS sensor or maybe CCD sensor, right? Mostly CMOS sensor. So CMOS sensor have some kind of a sensitivity for the IR, and if you remove IR filter, because almost all the cameras, including your iPhone or maybe Galaxy phone or maybe whatever Android phone, whatever it is. So all these smartphones comes with a camera, CMOS sensor, and on top of that you have IR blocking filter. So if you remove that, you can actually see IR, and then you know that if you just illuminate your hand or whatever the body part with IR, and then if you imagine it with using a camera, then you should be able to see the veins, right? The reason is veins absorb IR than your skin. Skin reflects, veins absorb, right? And uh, part of the radiations or the IR radiation that you emit will be absorbed by the superficial veins, and those area will be just darker than the remaining region. So when you enhance by using contrast enhancement algorithm, then you should be able to see your veins properly, right? So this is one image that I have produced using kind of an application with the IR emitter and IR camera, which I can just see the veins, right? It's a very simple application, and this is you enhance it, and then you create the image, and then you project it back to overlay it on top of the hand. Now you can give this one to phlebotomist, right? ලේ ගන්න කට්ටියට නැත්නම් blood draw කරන කට්ටියට එතකොට ඒගොල්ලන්ට මේක blood draw කරන්න එහෙම නැත්නම් කැනියුල එකක් plug කරගන්න හරිම ලේසි, right? Anyway, this may cost around couple of thousands of dollars, right? I have seen one in $7,000, and to build this whole the imaging, the apparatus is not here, but to build this one, it cost around 6,000 rupees, right? So to get to the projector, maybe you may need to another 30,000 to 40,000 at that day, maybe. So altogether less than 100,000 you can build this, right? Anyway, since it's medical equipment, should be expensive, right? You have to get lots of different certifications when you're going to provide this into hospital, right? So other applications include primary educations, for the visualization, right? It's not really anatomy, or maybe you can recreate the real anatomy of animals, human body, and then you can annotate them within the application, and you can just show it to the kids. Then they will, it will be easier them to learn. In the scanning applications, surgical simulation for treatment planning, right? So before the treatment, you can simply create 3D models by using the visualization applications, the visualization algorithms, and then you can perform the whatever the treatment to the simulation, and then see the result, and then you can plan it, right? Telemedicines nowadays, it's really popular, and this is another research area, right? Okay, why am I telling this the research areas, and why am I just distinguishing the all the things and also the new things and also the challenging parts? The reason is I know that some of you would like to maybe migrate, going abroad to do your higher studies, but I'm not a migrated, I know today's problem. So, or maybe you need to do kind of research for you as your final year project, right? Final year project so these are good areas, right? You can start with finding a topic, right? Without wait until somebody announces, okay, you need to find the topic and then go and search. Like demo පටන් ගන්න පුළුවන්. Special තේරුණා අනිවාර්යෙන් කරන්න වෙනවා. එතකොට ඒකට topic එකක් හොයාගන්න ලේසි. දැම්ම ඉඳන් මේ වගේ මෙතන තියෙන challenging areas මොනවද? Unsaturated අපි කියනවා අර saturate නම් එහෙම නැත්නම් ඒක දැනට හොඳට කියන්නේ matured area එකක් නේ. ඒකට ටිකක් අමාරුයි topic එකක් හොයාගන්න, but these are the areas you can find, because telemedicine is very trendy now, right? It's not the good area to do a PhD nowadays, right? But good for undergraduate or master levels. Telemedicine, interoperative visualizations in brain surgery, right? So, and also biopsy, industrial purposes, quality control, security. Maybe you know that textile for defect detection, even the metal industry for defect detection, especially heavy equipments. You can't simply see the internal cracks of metals, so you have to use X-ray, right? So just by X-ray you can't do that. You have to use visualization. So X-ray plus some visual computing, you can analyze the, where the cracks are and so on, right? But to do that, you need to have equipments and, security, another purpose. Now, if you can use, a very low dose X-ray machine, then you can penetrate, the clothes and find the internal, the stuff hiding, let's say, firearms like equipments, firearms like objects can be found from the outside, even without, touching uh, the subject, right? ඒ කියන්නේ අදාළ පුද්ගලයා අල්ලන්නේවත් නැතුව අපිට එළිය ඉඳන් මේක හොයන්න පුළුවන් සමහරට firearms තියනවාද, එහෙම නැත්නම් අර hazardous equipments තියනවාද, ඒ වගේ දේවල්, right? And not just X-rays, right? You can even use ultrasound, right? Or maybe some heat sensing equipments also can be used for the detection, right? And metal sensing detection, typically we don't use visualization, but the things that comes with visualization techniques, they give you reliable results, right? And another application is games with realistic 3D effects, right? And this is again a kind of, very trendy area, and it's a good, good area to even start a PhD, right? Why? It's really complex nowadays, and also it's really highly techy, and some parties actually kind of a saturated, well matured, and some parties actually kind of a virgin. Still, there are more ways to that you can explore, right? Maybe sometimes you may have the experience of Oculus devices, like Oculus Quest devices. They are really advanced in virtual reality, but still, when you play with those things, then you will find there are lots of things to improve, right? කොච්චර advanced වුණත් තාමත් දේවල් තියෙන. කියන්නේ සමහරලාට ඒවා use කරලා හිතන මේ technologies that exist, කියන්නේ මේ දැන්ද තියෙන technologies කියලා හිතන එච්චර futuristic technology, but still you can find the things to be improved. Okay, what are the domains, right? Biological scanners, electronic microscopes, and confocal microscopes. And these are just different types of microscopes. And applications, microscopic analysis, right? And paleontology analysis, and so on. Thermal imaging. So this is called FLIR imaging, right? FLIR cameras can sense thermal variations of objects, right? For an example, if you want to quickly get into the people who entered in the airport, those who are having, let's say, fever or not, then you can use this camera, right? Because it gives you the temperature of surface instantly, right? With a kind of visualization. This is kind of visualization, right? Okay, by the way, can you just name the applications of thermal imaging? I told you one, and what are the others? Any idea? Where else do you use thermal imaging? Maybe you have seen in movies, yeah, military. Exactly, humidity mapping. Yeah, military, or we are using in military, right? I have seen yes, night vision. Oh, FLIR can be used in night vision. It's true, but yeah, gas detections also can be done, because if you have, the if the aperture of gas, or maybe the අපි කියන විවරය කියලා, විවරය පුංචි නම් ගොඩක් වෙලාවට gas detection එක එතන හොයාගන්න පුළුවන්. කියන්නේ temperature එක වෙනස් වෙන නිසා හොයන්න පුළුවන්. That's correct. සමහරවල් temperature gas කියන්නේ gases වල සමහර temperature එක වෙනස් නම් ඒත් හොයන්න. මොකද සාමාන්‍ය atmospheric gas එකට වැඩිය hazardous gases වල ගොඩක් වෙලාවට temperature එක වෙනස් වෙනවා. ඒකෙන් හොයන්න පුළුවන්. Correct. Typically for the gas detections we can use typically for the gas detection we can use dedicated gas sensors, right? Air sensors. Okay, for the security purpose, yeah, actually that FEV is kind of a security, right? It's actually kind of a medical security one. Okay, there's a problem with the night vision. What's the problem? The problem is, yeah, in order to see something, the object has to emit some, the thermal waves, right? ඒ කියන්නේ FLIR කියලා කියන්නේ අපි emit කරලා ගන්න. අපි emit කරලා reflection එකෙන් ගන්න දෙයක් නෙවෙයි. FLIR කියලා කියන්නේ object එක emit කරන එක utilize කරලා ඉවර වෙලා ඒක තමයි අපි පාවිච්චි කරන්නේ mapping එකට. ඒ කියන්නේ නැත්නම් visualization එකට පාවිච්චි කරන්නේ. Right? So most of these FLIR cameras are very expensive, especially when with the higher resolution. Higher resolution means you can even get 1 megapixel, right, for reasonable price. In most of the cases, you will find just maybe 120 pixel by 200 pixel for around couple of thousands. That means nowadays maybe just about 100,000, right? And there was a smartphone with this FLIR sensor, as I remember, S60, right? S60, I remember it's Cat. Yeah, it's from Cat, right? You know Cat. Cat S60. It's a smartphone, typical Android smartphone with FLIR sensor, right? With I think the recent one has even a rangefinder, laser rangefinder as well. So anyway, night vision, you can do night vision, but I'm not sure if there are some objects which does not emit any thermal wave, or maybe if even though they emit some thermal waves in which the amplitude is less than the threshold of the sensor, then you can't see them, right? For the night vision, it will be better if you use IR camera, which emits the IR, which cannot be seen by typical human eye, but still camera can see it. Especially it uses IR spectral biased sensors. We can say CMOS, CCD sensors are they typically can sense them. Humidity mapping is, as I remember, humidity mapping is the one of the industrial application where the thermal imaging is mostly used. In construction, right, you can use leaky pipes within submerged into the walls by using this thermal imaging techniques, right? When you look at a wall, then you can find colored spots, right, or maybe different thermal spots. From that you can find the leaking points and other things. Yes. And think of other applications as well, right? Now here I just give you the fever detection, right? And there are others as well. And talking about the research area here, right? So it would be better, right? There are the research available for converting these faces back into kind of a identifiable face, because here you can't see the actual face, right? And if you can just convert it back to a kind of identifiable face or recognizable face, that would be better, right? So there's a kind of deep learning or AI research, right? It shouldn't be very easy, right? But anyway, can be done up to certain level, and still it's kind of a research area. And also most of these cameras equipped with visible color image plus, or maybe IR emitter plus visible emitter plus real FLIR, or the real the emitted object emitted sensing technology. So mapping all these things together, overlaying all these things together is another research. And also superpixeling. We use superpixeling for enhancing the quality of image. When you are zooming it, it's typically used in visual images. That means visual spectral image. අපි සාමාන්‍යයෙන් පාවිච්චි කරන අපි visual spectrum එකේ ඒ range එකේ තියෙන images වලට පාවිච්චි කරන, but it can be applied even in thermal image as well, right? It's a different research area. maybe you can try adapting one of the existing, super pixeling. So it's not super pixel, it's called super resolution. Sorry, right? Super resolution. So you can use one of the super resolution technique to try out this, right? Yeah. So under the domain, this is one mathematical analysis, right? In the under the scientific computation domain, and ordinary or maybe partial differential equations were represented. We are using for the scientific computation, and finite element analysis. So we use finite element analysis to convert some real world phenomenon into a kind of mathematical model by using numerical kind of a numerical method, right? And supercomputer simulation. So what's the difference between visualization, graphics, and imaging? So imaging includes enhancing, analyzing, manipulating, even acquiring, and even storing 2D and 3D images. So that's imaging. Graphics mean how do you make pictures or digital image synthesizing. So it includes both sampling and illumination. So maybe you have done illumination models. Have you done illumination models under computer graphics? You should have, right? Under the computer graphics, illumination. As I remember, it was shading and illumination, right? So under the illumination models, you may have learned lighting models, right? What are the lighting models? Directional lights, point lights, right? Ambient lights, and then illumination. Under the illumination, you may learn about how to model the ambient light modeling and diffuse light modeling and specular light modeling and so on, right? So you need to just recap all these things. And under the visualization, exploration, transformation the data, right? So that means you explore the data and then you can transform it to a different form of the data, and then you view this data as images which actually reflects the kind of it reflects the fluctuation or maybe some kind of information out of the data that you are going to visualizing, right? So simply convert is a kind of a transformations of data into kind of something that you can see, right? So the relationship to the other fields. So visualization is not, you can't learn it alone. Why? There are lots of other things. What are the other things? Vision, right? So this is called actually computer vision and image processing or signal processing. Okay, I have one more question. What's the difference? These two? So this is computer vision, right? It's computer vision or CB. And this is image processing. So what's the difference? Is it really different? Or is it the same thing? Is it different or maybe the same thing? Computer vision and image processing. It's not the same thing, right? It's different, right? You will learn, okay. In image processing, we build an image. Okay. In computer vision, well, for the moment, I will accept that answer for the image processing. So then what about the computer vision? Okay, in CV, we are not building. Then what? What do we do? Well, it seems that you know the answer, but you have trouble in formulating. So that's the exact problem when you're facing answering questions in the exam, right? So you are writing maybe half or maybe full of a page just to convince me that you know the answer, just because you don't know the way of conveying it to me, right? So sometimes it works, but most of the time it doesn't. Okay, that's a good answer. AI is using in this CV, correct, right? Well, okay, to be precise, how do you actually answer that kind of a question? Image processing, you get an image as an input, you process it, right? You process it, and then your output again what is an image, right? You input an image, and then you process it, and then you output an image, right? Input and output both are images. In computer vision, you input an image or maybe whatever the visual data, it can be a video frame or maybe a complete video, but the output will be not an image, right? Because it's going to be kind of an interpretation, right? Kind of an interpretation. So that's the difference. Image processing, you get a signal and then you process it and you output a signal, because it's under signal processing, right? Signal processing තමයි අපිට image processing signal processing කියලා කියන image එකක් කියන්නේ signal එක, right? Computer vision is actually you get an image and then maybe you apply image processing or signal processing, whatever it is, plus artificial intelligence, right? You have to apply some kind of an intelligence, computational intelligence, and then you get a kind of an interpretation. So that's computer vision, right? They are not the same. And illumination engineering and optics, these all these things actually related to the visualization. Why? Because acquiring require to work with optics. For an example, Oculus Quest, right? Part of it's actually optics, right? The lenses are there and mapping is there, right? And correct focusing is there, and those actually under the optics. And if you're capturing an image, again optics are there, right? So the light guided through kind of a bunch of optical apparatus, so optics is there, right? And illumination engine is again another one, right? The sensor development, right? Sensor development including the hardware implementation and other things, and computational geometry. So this is one thing that we need to focus on in this course as well, computational geometry. And psychology cognition, that's another thing, right? Why? Because sometimes we may not be able to create the full range of colors. Sometimes you may not be able to recreate the real things that you can see in the real world, right? For an example, if you ever played computer games, right? Maybe 20 years back, right? Maybe you may have, right? Probably not. Yeah, it doesn't matter, right? අවුරුදු 20කට කලින් නම් අවුරුදු 15කට කලින් කියමු, just 15 years ago, the quality of graphics compared to today's graphics is not really good, right? It's not better, right? It's kind of a worse. But the thing is, at that time, the developers actually were using psychology and the cognition, right? They get the help from these two, right? Mostly the psychology, and not just that, the model of a human perceptual system or human visual system, and they utilize it to fake most of the real world effects within the computer, right? I'm not sure if you have ever played the early versions of Need for Speed, right? The car game, right? So it's really wonderful those time, right? I remember my experience was when I'm playing the game, right? It feels like you are actually seeing the effects of glasses, reflections, diffractions, refractions, and also the scattering of the light scattering, right? Even lens flare. What else? The shadows, right? They were really nice, really almost like the things that we experience in the real world, but they are not, right? But they are not in reality, right? If you just dig into the deep within in the computer side, It's simply faking it, right? It's, it's not the things happening in real time, but they have been pre-computed and then just showing, right? ඒ කියන්නේ සමහරට ඔයාලට glass එකේ reflection එක පේනවා. ඒ කියන්නේ කාය එකක් එනකොට ඒ කාය එකේ glass එකේ ඒ reflection එක පේනවා. නමුත් ඒ reflection එක ඇත්ත reflection එකක් නෙවෙයි. They are not really calculating the 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 directions of the light and tracing it back using maybe ray traversing technique or something like that. They're just showing an animation which is overlaid on top of the glass, just that, right? So the animation actually gives us the impression of, okay, it's actually moving. So whatever the light reflecting over there is moving according to the movement of the car, but it's not really that, right? But it really worked, right? It really worked at that time, but we need to work kind of a lot more in our side, but it worked. But nowadays, due to the advancements of hardware, right? Hardware and applied mathematics, right? This one and computational geometry. So we can almost recreate the stuff in the real world, right? I mean, real world phenomena, physical phenomena, right? Phenomena can be recreated digitally to create almost, to give the almost realistic effect. Now you may know that nowadays games, right? They are actually creating those effects real time, right? By using ray tracing, probably. Even by utilizing ray tracing, dedicated processors for ray tracing, RT cores within your graphic cards, right? For high-end graphic cards, they have dedicated processors, dedicated cores for producing these things, right? So that's the advancement of the field due to is a collection of field, not just one, but collection of field, right? So all these fields consist of, research areas, right? And engineering areas and so on, right? So you have now plenty of areas that you can dig into the deep. You can explore more by yourself because you are now third-year students, right? You have the potential to get to know something by your own. So because of that, don't expect us to give you everything. We are just showing the direction. So explore it by yourself. And okay, I think some of you get into the, the special degree course as well. So they will have more works to do because they will have another year to work. Okay, so anyway, this is all for our first day of the lecture, and I hope to give you more on this course. And obviously, you can post anything related to this course in the Google Classroom. I'm going to use Google Classroom as our learning management system because I'm more comfortable using it. And at the same time, I feel like it will be better for the students as well because when I put something on the Google Classroom, it will creating a notifications and will send it to you as soon as possible to the service, right? Unlike our own LMS. But anyway, it's up to you, right? If you really want me to put the materials in the LMS, then I can put them in the LMS. Doesn't matter, right? But still, we can still use the Google Classroom for the communication. Okay, any question? Any question?